So in the previous segment we took up the case of one special case of three fluid or wave transmission in three types of fluids. One special case we took, and in this segment we will consider 3 or 4 more special cases. Now the other one, the next one which we are going to see is where you have again the same situation. Rho 1 C1 is rho 3 C3, sorry, rho 3 C3. That means the same, there was some fluid media in which you are actually putting a partition sort of. And then here you have rho 2 C2 is of the order of rho 1 C1. Earlier we had a very high value of rho 2 C2, and now we have, they are comparable, same order of magnitude. And then yeah, this condition still exists. Sine of K2L is approximately equal to K2L. So a thin plate type of material you inserted. Now what is your intuition? What would happen in this case? From the expression, anyway you can get it. So the expression was alpha t was 4 times rho 1 C1 squared, I think, by rho 2 C2 squared K2L. I think this was the thing. This is an approximate solution. Okay. In fact, you should have got it from actually if you go up to this point, in fact even in the previous segment I didn't write the steps, so that is why from here it's very difficult to get the intuition which I am telling you to get. In fact, I'll erase this. I'll write the intermediate step. Okay, so while going through, if I go back from here, you came here, right? I just wrote it by skipping 2 steps, 2 levels of approximation, one for this and one for this. So because now you are having this not being there, it is changing, so we have to write an intermediate step. From there you should be able to see, and that I am going to write, and that will be alpha t will be 4 over 4 cos squared K2L rho 2 C2 over rho 1 C1 squared sine square K2L. So last time what happened was this term was very huge as compared to this, so this survived, the second term as a whole survived as compared to this, but now they have become almost comparable, and this is a small number because K2L is small. So this term now in a way is negligible as compared to this, and K square K2L almost becomes 1 because K2L is very small. So then it becomes almost equal to 1. Okay. So in that, so if you consider all the three expressions, so this is very less than 1. Then you are getting alpha t to be 1, and that is what I was talking about, see, this itself should give you that feeling that there is no impedance mismatch happening. They are almost same. The rho c value, the characteristic impedance of the region from where the wave is coming, it is again seeing the similar kind of impedance in the second part, and that is why most of the wave will go through. And in this, the individual values of rho and c could be different, okay, but the product, if they are of the comparable number, then it is almost equal to 1, and all the energy will be transmitted. So that's the second case which I was talking about. And the third case is when rho 1 c1 is not equal to now rho 3 c3. Okay, so this condition now we have removed, and rho 2 c2 is much larger than rho 1 c1. Yeah, and similarly again sine of k2l is approximately k2l, and cosine of k2l is approximately 1. So these are the conditions now. Now if you have this, then what you will get is alpha t. Again through that expression, if you go, you will reach an expression this. Okay. So you have seen this expression earlier, where we had only two fluids and the transmission loss was like that. When we had only two fluids, the transmission coefficient derived was like this. With this rho 3 c3s, you had rho 2 c2s. That means what? This intermediate thing which you have now put in is almost like it's not there. That means suppose you are in a situation, there are two fluids, you want to separate them out by some means, but you want in a way, I mean, just physically the fluids needs to be separated out. Then you can use some thin plate like that with rho 2 c2 much greater than rho 1 c1, then it will be as if there is no material in between, just the fluids are being separated. Okay, acoustically it is exactly like, here it's, I should say, approximate, depending on this thin condition or this small condition. So it is like the middle layer is not there, so you have separated out two fluids acoustically. Fine. So that's the third case. And the fourth case is you have rho 1 c1 not equal to rho 3 c3 again. Then the second one is again rho 2 c2 much larger than rho 1 c1 and rho 2 c2. Sorry, rho 3 c3. Then third condition is you have chosen k2l such that it becomes some integer multiple of pi. Okay. Now if you do that, if you put in the expression where you had yeah, this expression. Okay, then what you will get is for certain, now this will happen when, because L is fixed, suppose you have taken a particular length, then at certain frequencies this condition will happen, and then at such frequencies it is just transmitted independent of the thickness. Or you can say that if you want some frequency to be transmitted, you can choose its length of the middle layer properly, such that this condition satisfies. Right? Then again you will have transmission of sound. That means that particular layer, it need not be thin as such, it can be as thick as possible you want, but for that particular frequencies or near those frequencies, particular band, it's almost like getting transmitted. So, okay. And case 5 is just these two cases are same, okay, same, and third case is pi, means odd number multiple of pi over 2. Okay, so in this case your alpha t can be approximated as 4 rho 1 c1 rho 2 c2 over rho 2 c2 plus rho 1 c1 rho 3 c3 over rho 2 c2 squared. Okay, because your sine thing will go to 1 and cos will become 0, and from that expression you can come here. Now what you can do is think about choosing this rho 2 c2 in such a way that it is rho 1 c1 rho 3 c3 root. There is a geometric mean of that. Okay, if you put it there, oh sorry, so this square is not here. This was over the full thing. Okay. Now, if you do that, you will come again to the condition that alpha t will become 1. Okay, just substitute here. You will in this. Now, what does that mean? That if you can choose a material in such a way, when see rho 2 c2 is the in between material, so that let's start with this. So you had two separate media with rho 1 c1 and rho 3 c3. They are completely different materials, so you don't have this requirement that they should be same. They are completely different. Imagine this is air, this is say glass. Okay. Now if you choose rho 2 c2 in this way, then you are getting a transmission of 1 irrespective of thickness. For, or when I say irrespective of thickness, for a given frequency range anyways, because for which K2L becomes this is the condition anyways. So that means for those, if I am interested in some specific, like a band pass filter, I want that certain frequencies only should pass, then I should choose this length in such a way that and then length plus rho 2 C2 value, then for that frequency it will be just passing through, and that is actually done for optics in case of air and glass. If they need certain frequencies of light to completely pass through, they put a very thin layer of coating on the glass whose what do I call means thickness is chosen like this according to this, because frequency is known. So frequency is coming here, so your frequency of interest lies here. So you choose the L such that this condition is satisfied. Then you go to the material property. You have to create rho 2 C2 in such a way that this condition is satisfied, so that for that frequency this light simply passes through. Non-reflecting coatings, for given frequencies of light. Exactly in the same way they do. The same thing can be done for sound also. Okay. So these are the special cases, I think 4 special cases we discussed of 3 layered media. Okay. So for this segment we will stop here, and we will see you in the next segment with I think it is more or less done. So we will see with incidence of wave at different angles, not head on the normal incidence, but at some angle. See you in the next segment.